guess we're going to get started. George is here from Embrace to talk to us about that. I think there were supposed to be some other announcements from Rick, but unfortunately he didn't give them to me. So
you can do them at the end.
Yeah, don't all run off when the meeting's over, because I'm sure we may or may not have announcements at the end. But without further ado, we'll let George take over.
Okay, so I'd like to thank you very much for the invitation and for giving me the opportunity to really share what me and my team are doing with respect to programming for the cloud and using F-sharp, which is such a powerful language, and really think that it might be, the tool of choice for really tackling the problems such as cloud computations. So I'll just give you a brief outline of what we're going to be talking about today here. First, I will present you a little bit about the Embrace team and the company that is behind this effort. After that, I'm going to show you some basic stuff with respect to what Embrace is about. Then after that, I will be presenting to you the main building blocks that really are being used when someone programs with Embrace in order to make cloud computations. Some concluding remarks, and after that we're gonna cut to the chase with some demos that I have prepared for you. These are real demos showcasing what Embrace can do and really demonstrate the paradigm that Embrace offers you. Okay. So if in any case you want to make a question, of course, you can stop and really talk about that. It will be something interactive. So the Embrace comes from a company called nyc-fsharp. It's an ISV company situated in Greece right now. It's active in custom software development. So as far as technology specialization is concerned, we are a .NET framework specialists, and we really like to use F-sharp very much. We have been early adopters of both .NET framework and F-sharp as well. And moreover, we are also quite specialized in utilizing Silverlight, and we do also use Hibernate when we really want to deal with database stuff. Since we are active in custom software development, there are several fields that we have been active lately, and one of them is the application framework development. And since we are really fond of doing stuff like that, this is where Embrace was formed as a part of our R&D effort, and the fact that we really like to deal with application frameworks and construct our own when there's a necessity for that. Okay, so about Embrace. What is Embrace? Embrace is a software stack, and it's actually comprised of two main things. The first one is a framework. So we are dealing with a set that provides us a set of libraries and tools, and of course all the patterns and the paradigms that go with the usage of this kind of libraries. This is the first part. And there's also a second part which has to do with runtime. So Embrace also provides runtime, which is actually responsible for the deployment, the execution and the management of the cloud applications that we might have developed and we want them to run on the cloud. So in essence, you can really think of it as a small cloud OS, because it really has all of the components that an OS should have, meaning it has a scheduler, it has process isolation and stuff like that. Embrace is based on the .NET framework, and actually is based upon the power that the F-sharp language provides. And as you will see later on, as we will be presenting the building blocks that comprise Embrace, it's monadic structure that really helps us provide what Embrace provides. So it's really a .NET thing and an F-sharp thing per se. So what is not Embrace? It's not just an API or another library. So we're not talking about a set of, let's say, functions that you're going to use and you're going to interleave your code with. It's not something like that. Of course, Embrace provides certain functions that are useful for making your computations run, but its basis is not formed upon a set of predefined functions. So it's not just an API or another library. Moreover, it's not a new language. So this means that you don't have to learn a new language from start. If you're familiar with F-sharp, then Embrace will be very natural to use, and you can seamlessly integrate, migrate, sorry, to using Embrace. Moreover, it's not a compiler-specific language extension, so it's not something custom that you really have to install along with your compiler or with your IDE so that it will function. It's not something like that. And of course, it's not just a set of tools, or it doesn't need any third-party tools. So we're not talking about toolbox and some kind of middleware. We're talking about something that is going to be used extensively within your code. And it doesn't have any sort of dependencies, excluding, of course, the presence of the .NET framework. Okay, so about the programming experience and how someone is able to make his programming with Embrace. The building blocks for the cloud-based distributed computations are the following. It's actually two things. The first thing is a cloud model. So everything that has to do with respect to how algorithms and computations are being expressed using Embrace, these have to do with the usage of the cloud monad. So this is where the power of F-sharp comes to the front line. We are using what F-sharp calls computation expressions, which I guess you are all familiar with. And the cloud monad is such a thing, and it's very similar to asynchronous workflows, which is like the async monad. So there is a certain kind of, let's say, correspondence between what async does and semantics, along with what the cloud monad does and its semantics as well. So with the async monad, F-sharp provides a very elegant way to handle the thread pool, and it provides an abstraction as to which thread and what threads are being used in order to perform an asynchronous computation. So this is the same principle, the same idea with the cloud monad. So the place of the thread pool is being taken by the actual cluster of nodes that you may have available. Either these nodes being part of a private data center or a small farm that you may have on premise, which would be interconnected via a LAN. Or if you run Embrace and such computations in a cloud environment, like let's say Microsoft Azure or in Amazon or something like that. So the notion is the same. You have the pool of nodes available, and each node is available for the cloud monad to execute its workload. So the correspondence is thread and node, and thread pool and your cluster. So this is the first primitive that is being used. It's the cloud monad, and this has to do with the computation side of things. The second thing is the cloud ref. So it's again this a corresponding notion with what F-sharp provides, which are the refs, and one of the most important differences that the cloud ref has with respect to the refs that fsharp provides is that they are immutable. So cloud refs are being constructed and their values do not change during their life cycle. So this is one thing. Moreover, in order to handle cloud refs, Embrace provides two monadic operations, which are the new ref, with which you can construct cloud refs, and of course during the construction you provide the data that you want these refs to have, and the get ref, which dereferences the data. So these cloud refs are the building blocks for distributed data structures. And these distributed data structures have provide the illusion to the programmer that all of the data are being handled as one entity, when in fact this data can be distributed in the various machines that your cluster is comprised of. The cloud monad looks something like what you see here, cloud brace. As I said before, it's a programming primitive, and it's actually our unit of distribution, execution, and scheduling. So what someone writes inside the braces of the cloud monad is supposed to be executed somewhere in the cloud. And in the cloud, we mean in the cluster of the available nodes that we have provided to Embrace. So this monad has, of course, some composition semantics, and we have provided three ways in which someone can compose cloud monads. So it's one is the sequential way of things. The second is the parallel, and we also provide a third non-deterministic composition operator, as you will see later on. So something very simple. We're gonna browse through some code here, but we'll also see the code in action the exams I'm going to demonstrate to you later on. If someone would like to, write a certain function that will execute to the cloud, he could write something like what is being shown here, which is just a simple return value placed in the cloud monad. And if you write this to the Embrace shell, as I will show you later, you will see this kind of type signature. And as you can see, when someone encapsulates a certain calculation inside the cloud monad, it gets this iCloud type signature where the return type is being.
So it's percent Haskell.
Sorry?
So it's percent Haskell.
Yeah, you could say that, yes. So the notion and the way this thing operates is that when you execute this, it will be scheduled and it will be transferred by the runtime to a certain node if that is necessary, and it will provide the result back. Of course, however, if this function is not executed, it does not return a value, but it's just a computation, as it is when writing such stuff in fsharp as always. So there's nothing new or nothing changes here. So if we want to execute this, we write something like the following, which says let answer equals all of these things. So this run remote synchronously will send a quotation to the runtime for the execution. And as I said before, the function will be executed somewhere in the runtime's cloud-based worker pool. So somewhere in the node, it will execute and will send us the result back. Okay, so this is more or less a small diagram of how Embrace sees the nodes. So there are actually three kinds of resources that Embrace utilizes. The the first and the most important one, let's say, are the workers, are the actual nodes that are going to perform the computations that our functions tell them to do. Moreover, there are certain nodes that are actually consistent of the runtime, which we refer to these nodes as master nodes, and these nodes are responsible for the orchestration of the code and for persisting state, as I will explain to you later. And of course, we have some kind of storage because in order for Embrace to handle failure, we have some points where we persist the environment of each node, so that if the node fails, we can restore this environment and continue with our computation from the point that a certain node might have failed. Okay, so for the composition semantics, this block of code shows how we can compose cloud computations sequentially. So let's say that we have this ask-dip-thought function, which is a cloud function. And we have the get ultimate question answer function as well. So you can see that after the cloud race, we have a let bank binding. So let's see what happens here. So if we get that and we execute by using the last line, which says let result is equals cloud run remote synchronously. What will happen is the following. The get ultimate question answer begins its execution in some worker that the runtime is going to assign to. After that, Embrace finds the let bank binding, and when it sees that, the execution of ask-dip-thought function start executing potentially in some other worker, or it might be the same worker if the runtime decides to do so. So until the execution of this function, the get ultimate question answer function is suspended. So you have a sequential type of execution. So they do not run in parallel, they run synchronously. They wait, Embrace waits for ask-dip-thought to execute in order to pass the value back to the first time variable. So after this is returned, it is bound, as I said before, to the variable first time, and the rest of the computation continues. So the same thing happens for the second time. And after that, the result is provided back. So,
does the Embrace system do any automatic memorization, or if you're in other words, you're invoking ask-dip-thought. If that was a very complex operation, is there any, will it completely re-invoke it again?
Okay. For the time being, there is nothing like that being done. However, the thing is that since this thing is under constant implementation development, this is one of the things that we are in our roadmap to develop. Although it's not in the very in the very near future, because we have some other stuff to do. But the thing is that since we have a runtime that is really responsible and really able to handle all of the results from the computations, we can implement something like that quite easily. But as of now, it's not implemented. It's not there. Okay.
I have another question.
Yeah, sure.
By ask-dip-thought being a separate instance of the cloud expression, does that mean it's going to run on another machine, or is there anything here that says like how many machines it will be used to?
Okay. Well, every cloud function that is being run is being seen by the runtime as a separate process. It's like an OS thing. So the runtime makes scheduling decisions with respect to which nodes should get which workload to execute. So it's not something that is deterministic in nature. It really has to do with the decisions that the scheduler will take. And these scheduling decisions have to do, at least for now, with real-time metrics that are being gathered in specific time frames by the master node, which is the one responsible for making the scheduling decisions, with respect to workload of each node. So it really depends on finding the optimum node in order to execute the function as fast as possible. So it's not deterministic. It might really execute on the same node, it might not.
But it is the unit of scheduling.
Mm-hmm. So all of this as a single entity, as a block, is going to be moved around if necessary in order to be computed. That's an dimension.
So one computation always executed on single node?
It depends on the computation, because here in this example, you see at the get ultimate question answer, you see sequential composition of the first time and second time. You will see in the next slide that we also have a parallel operator for composition. So the get ultimate question answer, if it is in parallel, as you will see in the next slide, is going to be run in various nodes, but its main building blocks will be run in each node separately. So what I mean is that each function that is a cloud function is a scheduling unit, so it might be run on one node, or one node might run multiple of these instances, or it might run multiple such functions. So it's the main unit, but this does not mean that each unit should occupy one machine. One machine could really be responsible for executing 2 or 3 separate functions. It really depends on the runtime and the scheduling decisions that it's going to make.
One more question was more about, like, let's say one computation with data is physically located apart from each other, right? Yeah, so how you optimize it? How you optimize the calculation?
Okay, in order to do that, we use the cloud monolith construction to the cloud ref. So if you instantiate your big data in cloud refs, you provide the opportunity to the runtime to distribute not the data where the code is, but distribute the code where the data is. So if you have a small computation, a serial computation that really needs to be running data that are spun in various machines, the Embrace runtime will make copies of this code to the various machines where the data is situated, and will do these things in parallel. So this happens due to the fact that we use quotations and we are able to move around code and data as well, depending on the context. I don't know if I covered it.
What if inside one calculation, so you have first data, it's sequential, let's say it's sequential. You have first calculation with data on machine 1, and then second calculation, you have dependency on first calculation, and you need data on machine 2. So what do you do? You cannot run it in parallel, right?
Yes, if the algorithm is not cannot run in parallel and need synchronization points, yeah, you can do something about that. Means, if there are barriers, you cannot overcome this. It's part of the algorithm. It doesn't have to do with the technology. It has to do with the algorithm itself. So Embrace provides the constructs to really describe all of these things, but it's really up to the algorithm if it is highly parallelizable and scalable. If it's not, if you have dependencies on previous data, you have to do something about that. You can't do it. Okay, so for the parallel composition, in contrast to the previous example where these two functions would run sequentially, here they would be running parallel, which means that when Embrace sees this operator, it will spawn these two functions that will be running parallel in two instances. Either these instances would be different machines or different processes in the same machine. They would run concurrently, and after both of these functions return, they would provide their values to the first and second variables, and they would be, and this would be printed out as we can see there. So we have this parallel composition operator, and we also have the cloud parallel, which is a superset, an extension of this parallel composition, which signature you can see at the bottom. So you have multiple functions that you need to execute. You could also use cloud parallel as well. So these are the two parallel compositions Embrace provides. And moreover, we also have a non-deterministic operator, which we call cloud choice. And it's depicted here by the red symbols. And we need such an operator for non-deterministic computations. So, if, for instance, you have a problem where you search for certain values in a search space concurrently, and you want to stop the execution of all of the cloud instances, all the nodes, once one node finds a certain result, you can use the cloud choice in order to, when you get the result, to abort all of the other functions that are being run at this time. So this is a small example where you can say, let's say we want to use Bing and Google to translate a certain message, and we want the first translation that occurs to be returned to us, and cancel the other one. This is such an example.
So just about that, obviously the choice operator is going to, whatever the first result comes back is, it's going to cancel all the others.
Yes.
In the non-deterministic cases, is there also a way to cancel all or part of the running processes? Like if you're doing it sequentially and you decide for some other reason that, like let's say you're coding an app to respond to a certain threshold, and if it doesn't respond to that threshold, you just want to cancel out the operation. Is that doable, or is choice sort of, is that doable outside of choice? Or is choice just is there any sort of user or program-defined cancelability?
Not at this time. No. The cloud choice is the thing that really will tell you in an abstract way when to stop something. Now, if you have certain conditions inside your algorithm and you stop the execution by pausing or by sending an exception, that's another thing. But if you want to have an abstract mechanism where you can really make non-deterministic computations, this is the way, and really someone should fetch some kind of a result in order to make the cancellation.
Makes sense.
Okay. And now for the cloud refs. As we said before, cloud refs are the data primitives for the cloud, and it actually is a mechanism that we provide in order to alleviate what we call data sharding. So, as I said before, it really provides the cloud refs really provide the user, the programmer, that they are programming in a data structure that is one entity, but in fact it's being distributed in the various nodes of our cluster. And in order to do that, we have provided support for several distributed storage mechanisms that we really need. So the first one are simple files, so that in order to to have a persistence of this data, we use the file system of the underlying operating system. On the other hand, we also have for the Azure implementation that we have been testing, we are using the Azure blob storage as the underlying storage mechanism, and we are making some implementation progress with respect to using NoSQL databases as well. Of course, these are all abstracted and they are not seen by the programmer, but they are underlying under embrace. And of course, this is a mechanism in order to do what we say aggressive data caching. So by the use of this mechanism, the runtime is able to really make decisions with respect to which code blocks are being sent to which machines in order to ensure the most optimum data locality that can be available at the time of execution. So here we have a small code snippet with how someone could, for instance, make a distributed cloud, a cloud tree, distributed tree. So what we need to do is construct a type where each branch is a cloud ref itself, as you can see at the table here. And here you can see the implementation of a mod function of a cloud tree, and how this function really demonstrates the various operators that we provide for the cloud refs. So you can see here that at this let binding we reference the values of the tree ref, and then we do a simple pattern matching in order to make the mappings. So it's a very simple cloud map, let's say, a cloud ref map function. So, some key points for Embrace. One of the things that we find to be very interesting and very appealing to developers is the fact that it provides a quite streamlined and transparent cloud programming paradigm. So, it almost feels like, you write things like they would execute sequentially. And there is also an abstraction with respect to how someone could really express computations if they run in a distributed environment or in shared memory like what we have with async and threads. So there is really no need to make such kind of distinctions, because the runtime really provides all of the orchestration infrastructure that is needed in order to make decisions with respect to when code should be run in parallel inside a machine that might have, for instance, multiple cores, or should be distributed in the various nodes of the cluster. Moreover, it seems like it has a single node execution, and the debugging is quite easy using some tracing semantics that we provide with the Embrace shell that I'm going to show you. Moreover, the Embrace runtime really deals with the process and data flow orchestration between the various nodes. And as I said before, it constantly supervises and monitors process execution. It also checks the environment state of each node, and it also monitors all of the resource allocation that has to do with each node. So it really monitors the CPU usage, the network utilization, memory, and stuff like that. So it can really take decisions in real time as to which nodes should execute which parts of the code. And another thing that is very crucial is the fact that provides all of the underlying plumbing and infrastructure that is needed in order to distribute the code and state when a machine fails. So, for instance, if someone runs some computations that have been written with Embrace in Azure, and for some reason, one or more of the nodes that are executing the algorithm fail due to a hardware failure for whichever reason, Embrace really deals with that. And when Azure brings up a new node that, of course, is really empty of state, the Embrace really provides the mechanisms in order to reload this machine with the state that was previously persisted, and really continue the execution of the code without having to stop and start from the beginning. So there is an underlying mechanism for failure management, which is part of the Embrace runtime. Why should somebody might want to use Embrace? Which are the appealing points? We think that the most really the strongest point of Embrace with respect to the paradigm that it provides and the development experience that provides to developers is the fact that distribution orchestration has compositional properties, as we've shown before. And of course, this is all is based on the power of the computation expressions that fsharp provides. So the conceptual model is quite simple. The primitives are simple and quite straightforward, and they share notions from fsharp, which means that people that are familiar with fsharp will find it very seamless to write the code in Embrace. Moreover, it's quite lightweight and transparent. It's just it needs a few DLLs and some executables in order for it to run either on, as I said before, a private data center or some cloud provider. Moreover, the underlying cloud services, if they exist, are abstracted, so you don't need to have under consideration the fact that your code might run on-premise or in some kind of a cloud environment. Of course, it's based on managed code since it runs on .NET. And it's based, as I said before, on fsharp concepts and architecture. So if someone's familiar with that, it's a very good starting point to use Embrace. So about uses and applications, well, the first thing has to do with high-performance computing in general. So stuff that has to do with simulation engineering, or computational finance, or bioengineering, or other stuff that really have to do with big computations are a good candidate. Yes?
Are those areas where it is actually used or where it can potentially be used?
Well, as I will say to you further on, at this point, Embrace is on a beta stage. So there is not an actual case study where a certain company has used Embrace in order to make stuff like that. But from the standpoint of what kind of computations can be expressed with Embrace at first, and second, by some in-house experiments that we have done and some preliminary use cases that we are doing with companies that are of this kind of industry, we've seen that Embrace is a good candidate to be used in order to do high-performance computing. Actually, we have made some implementations with respect to linear algebra iterative solvers that have been encoded with Embrace and have shown quite good performance results with respect to scalability when running into distributed environment. So that's an actual use case that we have in mind. But you know, this is the basis for lots of simulations and engineering stuff. You know, because linear algebra and matrix manipulation, matrix vector stuff are the heart of these things. Yeah.
So in that vein, so when in those example case studies for linear algebra, I that respects locality.
Mm-hmm.
Okay, there's no machinery in the tool chain for enabling that sort of locality.
Well,
I mean, that's also, the type machinery for F-sharp, doesn't necessarily mean that very explicit per se.
yes, but I think that this also once more has to do with your algorithm. I mean,
Yeah, the locality of access pattern is whatever, depends on your algorithm.
yes.
But you still want to be able to reason about it, either way.
So this reason has to do with semantics that might be provided by Embrace in order to enforce that. That's what you mean.
Yeah. Or
Well,
help you understand when you may or may not have the locality beyond finding out empirically.
mhm. Well, if you are talking about locality with respect, let's say, to not having cache misses, so in the sense that you have made your distribution, and now you are in a certain node and you start to really have something optimized there, then this is beyond the scope of Embrace.
I mean, but the same techniques for good locality, in terms of splitting the work suitably for distributed computing, are some of the same ideas for the per node case.
Okay.
Yeah, but anyways, we don't have to go into detail.
Well, no, but in the same sense, the way that you can split your data using cloud refs will, in a sense, describe the kind of data locality that you want to enforce. So this is not being done by the cloud monad and the bindings, but it's being done by the way that you will fill up your data using the cloud refs. So if you do that, then with respect to which data are being used in each computation, the runtime will send this computation to the appropriate data. So if you split the data in a proficient and very efficient way, it's going to work well. If you don't do that,
Okay, that's good.
yeah.
So for example,
Oh, sorry.
so is MapReduce will be a good candidate to run on Embrace?
Yeah, actually, I have two demos with that. So we'll see how it really executes MapReduce and how MapReduce is being seen by Embrace. We'll see that in a few minutes.
Yeah, regarding to the locality issue, so are you be able to provide for the developers leverage to change the behavior of the scheduler?
So,
you have,
Is it usually in schedule?
yeah,
so you're asking if there is some kind of a way to affect the behavior of the scheduler. Right now, no, we don't have something like that. But you can really, how do we say that? I will show you that to the MapReduce example. You can really start describing the way the computations are going to be done. By doing that, you circumvent the scheduler. And what I mean is that is the following. If you provide a very simple implementation of a certain algorithm that you don't provide any specific, any specific instructions as to use a sync or to have conditions with respect to how much depth the tree should go and stuff like that, then it's up to the runtime to do its job. However, if you start describing that, you actually implicitly affect the way that the scheduler will take its decisions. But if you do that, you compromise the clarity of the code, which is something that you might want to do or you might not want to do. It really depends on your needs and if performance is the first, thing that you have to have satisfied, or the clarity, or something in between.
Engineering time versus
Sorry?
I mean, engineering time versus
Yeah, exactly that. It really depends on the problem and what you are willing to sacrifice. Of course, we have in our mind to provide a way in order to affect scheduling decisions when the code is being run. And we can do that because of the fact that there's a runtime involved in the middle of all of these computations. So there are very interesting stuff that you can do, such as while the code is running, you can really change a part of the code, which we call code swapping, or you might instruct the runtime to start giving you back a trace of variables and variable data of a certain node or of certain nodes. So in that essence, there is the infrastructure, Embrace has the infrastructure to provide such a mechanism as well. But as of now, it's not there right now. Okay. And of course, the other very good candidate class of problems for Embrace is the big data thing. So MapReduce algorithms are also good candidates for Embrace to execute, which of course, as you know, have various usages like data mining or web crawling or graph traversal or document clustering and stuff like that. So the big data thing is also another very good field where Embrace might come up handy. And the big issue and the big power of Embrace has to do with the fact that it doesn't really have to be one thing or the other thing, but you can really combine stuff that has to do with big data and big computations if you see this fit. So due to this expressiveness, you are not confined in certain paradigms that might be very fit for some applications, but not so convenient for other applications. Okay, so for now, what Embrace really supports are distributed computations and distributed data, of course, with the cloud refs. There is also a very good and a very solid infrastructure with respect to exception management, and this can be a really big issue when you have lots of machines running and you have exceptions occurring in some of these machines, and the administrator or the developer has to be notified about these exceptions. So we have an exception management policy here. Of course, fault tolerance is another thing. So Embrace actually now supports environments that that may provide faults either from hardware or for some other reason. Moreover, we provide a mechanism where you can have local testing and debugging, which is something that I'm going to show you in this demo actually. And we also have a Windows Azure implementation for everyone that might want to install Embrace in Azure and make its computations run from there. And as a very as a roadmap for the very near future, we want to provide support for more cloud platforms. We have Amazon is what we are testing right now, so that we can really provide Amazon support as well. Moreover, we are checking out the compatibility of Embrace with respect to Mono, so that we won't be confined to Windows servers. And we also want to provide, to implement some link providers for Embrace in order to provide the opportunity to programmers using C-sharp, for example, to utilize a subset of Embrace. And moreover, we want to provide some stuff with respect to integration with Hadoop and to GPU. So this is for the near future. Yeah.
So is the goal to be able to have like one program and run on many platforms, or would they be very different?
So you're asking if there's going to be some kind of code porting? No, the notion is that you won't have to really change stuff with respect to your code, except might be for stuff that have to do with, let's say, URIs or something that might be specific as to how it's described between platforms. But other than that, with respect to what kind of code you run and if it should be necessary to modify something from there, no. The notion is that you shouldn't modify anything. And from what you have seen, don't need to change something. And what we really need now, since we are very near our beta release, we are planning to have this release at the end of this year. We really need opinions and feedback to see how this project really stands up to the challenges that someone might have in order, to make programming for the cloud. And another thing is usage and testing. So we are really looking for either people that deal with, real life problems, that know in detail the difficulties that exist when someone needs to write code that will execute in a distributed environment. And other than that, institutions and firms that really rely into big computation and big data manipulation, so that from their experience we can see if Embrace, really tackles the problem with the elegance that we think that it should do, And of course, funding and investment for such a project is always welcome, but okay.
Or consulting firms, that probably would be a little bit easier to secure in some way.
So,
I mean, just as an alternative way of doing funding.
oh, yes, of course. Yes, this is another way as well. By seeking to find people that would really think that Embrace might solve some of their needs, it could serve something like what you described.
It's another, that's sort of what I'm trying to do with my stuff.
Okay. So, do you have any other questions maybe? I guess not. Okay, so let's dive into some code then.
Do you have any case studies where you can also compare how your version of something works versus sort of other ways you might try and do it?
This is part of the QA that we are doing right now, because I didn't say that, but I will elaborate a bit on this. For this beta release, what we do are the following stuff. We are building at first a good documentation base, and this documentation doesn't have to do only with providing the ways that someone can use Embrace to make an algorithm, but provide some algorithms as a starting point for people to elaborate and develop their own version. So as a part of that, we have been making tests with other platforms as well, and some preliminary tests that we did had to do with what Microsoft provides now as some free instances of Azure with Hadoop. And we managed to run some MapReduce algorithms that were run at first with Embrace, and at second with Hadoop using the streaming API that Hadoop provides in order for someone to integrate Hadoop with another language like C# or F#. And the results we have from that tests are very encouraging. We have seen that
Or like still needs tuning, or you do better?
with the streaming we do better. If a strict Java implementation is being used, we are slightly worse. And we are really trying to see.